Hi everybody, as you just heard, my name is Moises. I'm majoring in biochem. I am an analytical student. I'm transferring to Cal Poly in the fall. And I'm here with my mentor Catherine and my faculty advisor Raman Microscope, who's not present today. And we're working to use surface enhanced Raman spectroscopy to detect relevant small molecules. So, let me give you guys a brief explanation of what SERS is. Well, you guys have already heard a great explanation from Valentina right now, so I thank her for that. So, what is surface enhanced Raman spectroscopy, or SERS? So it's a type of vibrational spectroscopy that can detect molecular information. So in other words, it can create fingerprints of certain ketone or molecules. As you can see here on this diagram, a laser will hit molecules and excite them and relatively give off a signal. However, since Raman itself is very weak, we need to use surface enhanced nanometallic structures to enhance our signal. In our case, I've been using mostly silver, but I'll talk about more of that and more in this presentation. And essentially what we want to do with all this information that we collect, we want to collect libraries of this and essentially create a target breathalyzer that can detect these diseases non-invasively. And I'll go more into detail on this next slide about what kind of diseases we can detect. So what you see here are structures of ketones. Now these ketones are relative to diabetes themselves. So ketones are formed when there are low blood sugar, when sugars are not, when there's like not enough sugar in the body. And for diabetics, it causes them diabetic ketoacidosis. So what I'm doing is detecting each of these molecules first individually to begin creating, like I said before, a library. As I continue on with my project, I'm later going to move on into more complex mixtures of these ketones. So in a blood sample of diabetes, you don't just find one ketone, it's actually a mixture of many. So to better mimic these samples, we want to create a mixture of all of them together to essentially get a better understanding of these spectra that we'll collect. So, the Raman Microscope. This is what Valentina and I actually use on our work. As you can see here, this giant box right here. I'll zoom in a bit. It's actually more like a compound microscope. On the side right there is a computer where we actually collect all of our data. And when we zoom in, we can actually see it's just a regular compound microscope, except on the objectives, there's actually a laser that will hit the molecules and create the information that we need. So, what is it what are these nanometallic structures that I'm talking about? What are they and how do I work with them? So this is what they look like. This is a picture that was given to me by my mentor Catherine. These are actually silver coated metallic structures. These are what I use for my everyday experiments. Now, for us they seem flat, but when we actually zoom in on a nanoscale and then from an electron microscope, we can actually see that they have built-in silicon wafers. Now, these wafers are actually what creates hotspots for us, and this actually allows us to concentrate the electric field around our molecules so we can better find the data that we're searching for. This is actually a schematic of what it looks like. So instead of us looking everywhere on the nanometallic structure, looking for the data, we can actually just choose any spot. And like as I mentioned before, the metals that we're using are gold and silver. Now the metal that I'm mostly working with is silver. There's nothing wrong with gold. Gold is actually an excellent metal to be working with, but since silver has a higher electroconductivity than gold, then more preferably we're using silver in my case. So, if you observe the schematic right here, I'll show you more into detail of how the Raman microscope works. So, when the laser hits the molecules on the nanoscale metallic substrate, it will actually scatter light. Now, this light is then collected to determine the Raman shifts of the data that we see. And it's represented in intensity versus wave number, as you'll see in the graph that has appeared right there. Now these shifts of these ketones have same characteristic regions, but each of them is unique. So for example, all of us have unique fingerprints. We're identified by our fingerprints, and so is each spectrum of each ketone. They each have its own spectrum that uniquely identifies it to itself. So this is actually data that I've collected through these past 8 weeks. On top, you'll see my data is from pure liquids, and on the bottom is liquids on silver substrates. Now, focusing on the top data, we see that the peaks, the spectrum versus the spectrum on the bottom are relatively different. On the top one, I actually use capillary tubes. They're just simple, small, skinny little tubes that I actually put in the liquid itself and put it under the microscope with nothing added, just simple ketones themselves. And I did this just to collect a library, just to collect what should I expect when I collect the data. On the bottom, we actually see the data represented when I put them overnight in millimolar solutions. So I took the silver substrates that you just saw, and I put them in each of these ketones, depending on which one I was working with, acetoacetone, cyclopentanone, or hydroxybutanone. I left them overnight, and then on the next day, I put them underneath the microscope. And this is the data that I got from them. As you can see, there are differences in between both of these graphs, but this is normal because on the bottom ones, they're actually in an environment of the silver. The silver is what causes these relevant shifts to create these different peaks. And on the top one, you see that there is no environmental influence in it. So those are relatively just pure liquids, and these are the ones that are changed because of the environment. So on the top one, we see this is actually a mixture of all three liquids together. As I mentioned before, blood samples and breath samples contain more than one ketone itself. It's actually a mixture of many ketones. So to better mimic that, I actually did a drop and dry technique on the top graph, and I got this complexity of a graph. And now this is good. We want this so we can better understand what we need to look for in the future. And I brought this graph back up from the previous slide to see if we can find similar peaks in between them. There are certain regions where we see similar peaks. However, we see that there are a lot more different peaks on top than there are on the bottom. We can quantify this data and observe how much of each ketone is on the data above using math analysis. I don't know how to use that part because I haven't been introduced to it. But essentially, we can see how much of each ketone is presented there. And also the different peaks can also represent the different mixtures of two different ketones. So maybe not all three of them are together, maybe it's just two of them in one peak, and so on. So this is actually, as I progress through the 8-week course, this are actually my gas phase trials. These are actually they're kind of different. I've had some troubles with them, but as you can see here, these are like the best graphs that I've gotten for the past few weeks. You can see there's arrows on the black line and on the orange one because they're on a different intensity. So there's a 2y axis plot on them. Now, essentially, we want to, my target goal was to create a breathalyzer that can detect these diseases, that can detect these ketones. So these are actually the gas phase trials. These are actually Spectra that I got from this new model that was introduced to me. It's hard to explain how the process goes, but bear with me. So a substrate is placed inside this kind of square, and it's pressurized underneath a rubber band, and with two filled wells filled in with the ketones. We leave it like 4 to 6 hours or overnight, and essentially some of it will evaporate and will land on the substrate. These are actually the ones that we just recently gotten. It's still early trials, so I'm still going to further more. I'm still analyzing these a little bit more, so these are like very early trials, so we're still working on this more. So as I continue on working with this, I want to essentially increase the complexity to better understand the different structures of the ketones found in breath samples. So I'm going to continue working with complex mixtures, getting better data, getting a better library. And then eventually I want to decrease the concentration of each millimolar solution to better mimic that of biological relevant concentrations, for example, blood or breath samples. And I'm going to also continue with the gas phase trials, and then in the future I will use water vapor that will better mimic our breath samples. And so to conclude all this, we wanted to show that surface enhanced Raman spectroscopy can actually detect these biomarkers, and we can essentially use them to create a breathalyzer system. So I want to thank especially my mentor, Catherine. After I lost track of how many questions I've asked her when I reached 1 million. So I want to thank her for being very patient with me. My faculty advisor, Martin Voskowitz, and all the Moskowitz group members, especially Jose Navarrete, who spent some of his time helping me with my presentation skills, because trust me, I was a nervous wreck. So. Wendy Ibsen, thank you so much, and Jens, of course, and all of Photonics group members. You guys helped me out a bunch. It was great to know all of you guys. Thank you.